Iraq War has done a lot worse.
Really?
Yeah, a lot worse. We're seeing networks with hundreds of attacks per day.
There are a lot of kids who just think it's fun.
Right, and they're
taking advantage of it, but there's a lot more other stuff.
Yeah.
Right.
So you don't think it is just kids?
No, it's not just kids.
Do you have originations? Do you have origination points?
A lot of the difficult to track ones are the ones where you run those sports scanners for a while, find a lot of computers that you can leverage,
Right.
and then all those computers send traffic out.
So the zombies?
Zombies,
Zombies,
yeah. And so,
What is this going on?
So the hardware was one aspect, and once we had the architecture together, we built it to spec to say up to 1 million concurrent flows on a gigabit type connection, and be able to look at all the payloads and all packets, not just sample and all that stuff. The second challenge was, how do you tell this hardware engine what a application flow looks like? And some history, the only type of applications that needed to deal with this were applications like firewalls. Checkpoint, Firewall 1 has got some stateful capabilities into it. But the way to tell it what an application looks like was to do some packet scripting. So you'd write a script saying, if this packet comes in, expect either that or the other, and if that comes in. And that is good for, at the time they have to deal with FTP.
Yeah.
You can kind of get away with it for FTP. But for more complex protocols, cluster IP, look at H323, there's a lot of those peer-to-peer stuff. By the time you finish writing enough packet level rules to get this done, it's over. There's 3 new protocols. This one's obsolete. So we've had to create some level of abstraction. So just like the programming languages hide all the internals of the processor and the registers, and our abstraction hides the fact that this is all running on packets. It knows the concept of flows. It makes it very easy to create an abstraction of those method exchanges and the syntax, and not worry about the underlying transport. And then you compile it down to the millions of packet level rules that our hardware can then execute it.
So you're all IP, you're not IPX. Saying IP?
Yeah.
And how did you build your own ASICs, or did you leverage your processor?
We tried to leverage an off-the-shelf network processor, and it doesn't work because all those guys are layer 3, 4 that optimize the hell out of table lookups and header processing. They have almost no data buses, very small program stores, because they're targeting the mass market, which is routers and switches. And we looked at 1 million contexts. How do you even take a network processor and have it didn't work, so we had to develop our own.
So the element management systems won't help you at all?
Element management in terms of?
The network element management systems for you to get the traffic, and that's a lower level, so you just have to have totally new infrastructure.
Right.
What is the typical ratio of service engines to the routers?
So if you look at the device I showed earlier, a pizza box would handle a gigabit, full duplex, gigabit of traffic. So we have smaller boxes and we're building bigger boxes. But if you look at that, then there's typically quite a lot of access equipment aggregating, terminating sessions, aggregating it, doing some basic mission control before it hits a router blade that takes gigabit. So if you look at a ratio, I don't know what the right answer would be, but there'll be a few of those compared to a lot of the transport gear.
Now you're saying you're counting every single one. Couldn't you do some kind of optimization and somehow get 10 flows in that are identical and then just throw away 9 and then say it's 10, it's 10?
Yeah, a lot of this is configurable, and in fact, if there are a lot of flows that you don't even care about, you don't have to look at all of them in depth. And for some of them, you just want to monitor statistics. Again, you can sample. But a lot of the hard work is when a session gets started, because then you have to figure out what it is, what it's trying to do. Once that's done and the connection is established and the data is flowing, then then monitoring the data is easy. That's all hardware.
So on very short connections is what would kill you.
A lot of very
Short-
short connections would be the most stressful.
So the point-to-point, which have very long duration connections, are pretty good for you.
Yes and no, because a lot of those protocols have very short setups in a different connection for data. But there's a lot of those, and initially some of them were really badly designed. And so there was the first generation of even Kazaa, I think, it was Fastnet or whatever. What they did was periodically send up an update message so that all peers still knew who all the other peers were. And there wasn't that much peer-to-peer traffic, but that periodic boom of sync messages would bring the network down. So there's a lot of... I'll skip those. Conceptually, it means instead of working your way bottom up, you want to conceptualize and then compile down. And then I just brought in a few snippets of what this code looks like, the language looks like. So this is the amount of code it would take. This is when ISP said, first time in the day you come in to the network, you're trying to go somewhere for content, and it depends how you want to limit this. You get redirected to the ISP's portal, which says, welcome, here's today's office or whatever. And then next time, you just go through. And the way this is done, by the way, is we recognize this flow, we intervene, and you're trying to get to CNN.com, so we change the flow destination to go to ISP.com. And from a user perspective, it's transparent. From the network, we just hijack your flow. We can do this for movies, for games. It's a way in prepaid to say, sometimes advice of charge. You only have 3 more minutes. Do you want to buy more, press here, or do you want to just keep going, press here to continue? Could be used for a lot of things. Another example is in one case where there was some need to do some kind of control on which sites you could go into. And it's not very difficult, but we wrote it in C++ and it was like hundreds of lines. The equivalent in SML was, yeah. Now when you compile this,
a high-level abstraction.
yeah, when you compile, because it already assumes, it knows what a flow is, it knows what, you compile it, it will break down into millions of lines. So we have this whole development environment, and there's the control tools. But at this level, and there's templates and libraries just like there is for C++ and Java, so you have to create this all every time from scratch. But then you have this built-in editor, compiler, integrated environment. The compiler compiles into this intermediate representation, which is a fairly complex graph, on which we run optimizations. And then the back end could either, we've written 2 backends. One is that compiles into our hardware, which scales. The other is for plain Pentium.
Wow.
Works the same, fraction of the performance, but if you want to use this at the enterprise, or and you could write backends for other network devices.
And what's the ratio of performance?
1 to 10.
Is it?
Yeah. Sometimes even more.
Yeah.
But for some places you don't need a lot. For some applications, you don't need to look at all the flows. You just want to do something for voice over IP. So compile this to a machine that just looks at the voice over IP.
But over time, the Intel processor is getting faster and faster and faster.
Those processes are leveraged in our architecture for all their general purpose stuff. But if you look at the specialized tasks that you need to do, general purpose has a lot of overhead.
It's I/O that matters, not CPU.
Yeah.
I/O,
Yeah.
memory.
Yep.
Speed of the CPU is almost.
And then what's the
Back to Fuse.
OS? Linux?
We use VxWorks
Everybody
right
doesn't
now.
really understand it, this Intel, I can tell you.
It's nothing
They don't understand
specific
it.
in VxWorks that we need to be Linux.
So you said you're not monitoring the flows like at vSLAM level, and in typical carrier architecture you have a broadband remote access,
Right.
an aggregator. Those bandwidths tend to be 10, 20, or even 40 gig capacity. So it sounds like you need several service engines for each of those aggregators.
Yes, the 40 gigabit is typically not, we don't see a lot of 10 gig Ethernet type connections or OC 192 at the edge. That's deeper in the core. So you'll have a lot of disparate connections that aggregate into a gig link or OC 48, which will then run through our box. And a lot of those physical connections, while they may have 40 of them, are not really heavily utilized. So often you can aggregate several of them into one box. And then this is something you could use next to the vSlam. In fact, we are. It's small enough, it can create some local service interaction.
So you need to have redirected traffic from an IP flow that once you get to conversion to an ATM link, you're out of the picture.
Our bet was that IP is the game, so we stayed away from ATM. It's not impossible to do, but and I think it was a good bet. So where this becomes interesting around the vSlam is for IP-enabled vSlams. And if you look at the big vendors, Alcatel, Lucent, UT Starcom, they're all putting IP into the vSlam because growth of just pure vSlam ports is not that huge.
But transferring to the user, it's all encapsulated in ATM in many cases anyway.
In many cases, what they want to do is to have local content at the central office. Then coming off the vSlam, you get served this content, and it's perfect quality because you don't have to go anywhere to get it. But they still need something to control access to this content, meter it, and monetize it.
So it sounds like you need to be closer to the vSlam than to the aggregator.
For this kind of service, yes. Some put the content next to the aggregation device. We sit next to the aggregator. And I think most likely a lot of those IP connections from the vSlams will be aggregated over a Metro Ethernet infrastructure, which is going to be very cheap. And that's going to throw ATM out the door. So again, I think we're almost done. This is the development environment, compiler, debugger, profiler. It's actually pretty cool. You can debug.
Yeah.
You can record real traffic on your link, run it through a simulator, debug your service logic, put a breakpoint on certain types of packets or events, and see what happens. Yeah.
I just want to know who invented SNL. You guys did?
Yeah.
Oh, okay. I didn't.
Yeah. It's part of what we had to create for this whole thing to work. In terms of performance, it's typically what do you want, flexibility or performance. It was really hard to say yes, just both. You can't give up performance because at the aggregation point, there's going to be a lot of traffic. And at the same time, without flexibility, this thing's going to be a dud. So that's been done.
What kind of technology did you use to write your compiler? Is it Yak or C or what?
Yeah, so parts of it is C, parts of it are Java, and Yak and stuff like that. You use always for the. Yeah, but we've created this mechanism where you can mix SML with Java or C++. So you have callbacks and you can write your own generic. So just the last two slides where we think this will go next. So we assume once there's an intelligent device in the network, once it's already doing all the heavy lifting for profiling the traffic by application, by flow, by session, and recording all the application level events,